All right, let's dive right into this explainer and learn how to solve the ultimate DevOps mystery, saving a crashing Linux server. Look, if you work in tech, you know that keeping your applications up and running 24/7 is basically priority number one. But what happens when the very infrastructure hosting your apps just starts failing? Well, today we're putting on our detective hats. We're going to walk through the exact strategies, the tools, and the command line tricks you need to manage Linux processes like an absolute pro. So picture this. You're managing a massive fleet of Amazon EC2 instances. It's the middle of the workday, traffic is spiking, and suddenly your system just hangs. Alerts are literally firing off left and right, CPU utilization is pegged at 100%, and nobody, not even you, can properly log in. This isn't just some theoretical exercise, right? This is a daily, high-stress reality in IT operations. When that server freezes, you've got to act fast. But more importantly, you need to know exactly what you're looking for. And this brilliantly illustrates our classic nightmare scenario. What we're usually dealing with is something like a multi-threaded Java application that has just completely gone rogue. As you can see, it's hoarding 90% of the system's memory, leaving your critical Nginx web server basically starving for resources. Eventually, that web server is going to throw an out-of-memory error and crash. The crazy part? The underlying hardware is totally fine. But the software is fighting this brutal, invisible war for CPU and memory. Okay, to solve this crisis, we first need to quickly revisit the fundamental building block of a Linux system. Literally everything that runs on your server, whether it's that rogue Java app, a quick shell script, or a massive AI model, is categorized by the operating system as a process. A process is simply a running instance of any program. You see, software applications can't just talk directly to the hardware. They have to go through the operating system, which acts like a manager, carefully handing out CPU and memory to all these individual processes. All right, phase one, the reconnaissance. It's time to deploy our live security cameras. We've got two main observation tools at our disposal here to observe the crime scene. First up, we can use the top command. This gives us a really raw, real-time data feed of system performance, updating every single second to show exactly which processes are eating up the CPU and memory. It's great, but if you want something a bit easier to read in a panic, you can use its visually enhanced cousin, htop. Now, htop gives you the exact same critical data, but it wraps it in this colorful, super user-friendly interface with nice little bar charts for your resource utilization. Real game changer. Moving on to phase two, the interrogation. We are hunting our suspect. So the real trick here is dynamically translating what we want to do into the command line. We start by firing off PSAX, which asks Linux to list literally every single process running right now. But as you probably know, that list can be thousands of lines long. So we use the pipe symbol to forward that massive output straight into grep Java. This tells the system, hey, filter exclusively for the word Java. And then we use a brilliant little pro tip, grep-v grep. Since your search command itself actually contains the word Java, Linux registers your search as a Java process too. Adding that -v flag just filters your own search out, leaving you with exactly what you're hunting for. Now, what's really interesting about this breakdown is how cleanly it organizes the PSAUX output. Once we filter down to our target, we get this perfect table of evidence. We can see exactly who started the process, in this case, the root user. We can see the CPU load is pegged at a terrifying 99%, and I can even see the exact triggering command that spawned the app in the first place. But listen, the absolute holy grail of evidence we extract from that table is the PID, or process ID. The PID is a totally unique numerical identity assigned to every single running process on your server. It's essentially the fingerprint of the process. You could honestly have 100 different Java applications running on the exact same server, but each one gets its own unique PID. And this number is exactly what we need to finally take action against our rogue application. Which brings us to phase three, the takedown. Let's neutralize this threat. As DevOps pros, we follow a really clear incident response path here. Step one, locate the PID, which we just nailed down. Step two, we use the kill command followed by that PID. Now, standard kill is actually just a polite request for the process to terminate gracefully, letting it save data and close its files. Oh, and by the way, if a rogue app has spawned dozens of identical processes, you definitely don't want to kill them one by one. You just use killall followed by the program name, like killall Java, to politely shut them all down at once. But what if it stubbornly refuses your polite requests? Well, that's when we bring out the heavy artillery.
And that heavy artillery is the number 9. When you add a -9 to your command, making it kill-9, you skip the pleasantries entirely. It sends a signal directly to the Linux kernel to forcefully override any background tasks and just instantly obliterate that hung process from your system. Seriously, it's the ultimate trump card when you're dealing with a totally frozen server.
But hey, it's worth noting that the kill command is actually a super versatile communication tool. It sends different signals to your processes. For example, kill-3 doesn't actually destroy the process at all. It extracts thread dumps. That is an absolute goldmine for your developers trying to figure out why their code went rogue to begin with. Or if you just want to hit pause on the chaos without losing any data, you can throw a kill-stop. Once the server stabilizes, you just wake the process right back up with kill-cont, and it resumes like nothing happened.
Okay, crisis averted. Phase 4, the aftermath, managing CPU prioritization.
Now, let's look at a totally different scenario. What if that heavy process is completely legitimate? Say it's a massive scheduled AI calculation that absolutely needs to run, but it's just taking up way too much room and choking your actual web traffic. We obviously don't want to kill it, but we can't let it ruin the user experience either. To fix this, we have to understand how the CPU thinks. By default, the CPU assumes any process demanding tons of compute time is highly important. As one of our sources so perfectly put it, the CPU algorithm is like a doctor. A doctor prioritizes patients in the ICU over others. So the CPU sees that heavy process and rushes all its attention over to it, assuming it's a total emergency.
And this is exactly where you expand your management toolkit. As a Linux admin, you have the power to step in and override the CPU's default assumptions using a command called renice. By running renice on a specific PID, you manually deprioritize that heavy task. You're basically whispering to the CPU, hey, I know this task is being super loud, but just ignore it for a bit and focus on keeping the web server alive. It is a completely brilliant way to balance server load without having to terminate important background work. Finally, as we evaluate our overall server health, we've got to distinguish how different processes run. Standard processes usually run in the foreground, right? They completely lock up your terminal window until they finish. Now, if you append an ampersand to your command, you can push them into the background and keep working. But here's the catch. Whether they're in the foreground or background, standard processes will die forever if the server crashes. That is where system services come into play, things like our Nginx web server. These are special, highly configured background tasks designed to automatically resurrect themselves if the whole machine happens to reboot. Knowing the difference between the two is absolutely vital for your long-term reliability. So there you have it. You now possess the ultimate DevOps Detectives Toolkit. From top and PSAOX to killall, kill9, and renice, you know exactly how to investigate, manage, and ultimately save a crashing Linux server. But remember, in the 24/7 world of IT operations, systems are literally always changing. You save the server today, but what unpredictable rogue process is going to try and take down your system tomorrow? Keep your monitoring tools sharp and your command line skills even sharper. Thanks so much